track. Just a special mention for all speakers that want to be kind of cabled up with a wireless microphone. If we can ask you to go over to the AV desk just when the previous speaker starts his Q&A session. That'll give us enough time to get mic'd up until a better transition. Okay.
Okay. So our first speaker, welcome Aaron. Aaron Lombrozo from Sandia National Laboratories. He's a control system engineer working there. He's going to talk about a very appealing title, Orchestrating a System. So.
Hi, my name is Aaron Lombrozo. I work at Sandia National Labs at a large pulse power accelerator facility called the Z Machine. For more information, look on Wikipedia. Won't be covering that. So I'll be talking about how we tie together a bunch of our systems, keeping things flexible, maintainable, all that fun stuff. So here is a picture of the top of the Z Machine. It's a large pulse power accelerator. It's got a lot of stored energy, basically funnels it all into a small chamber and generates roughly 2.5 megajoules of X-rays over a very short time period. So you get a lot of radiated power with these X-rays. We do tons of sciencey things, but control systems, you don't care about that. Does make cool pictures though. So this is all the electricity that didn't make it to the target. You can kind of see it's branching off, trying to find any place it can get to ground. Makes a great picture. We try to get rid of most of this over the years. Next door to this facility, we have a lot of pulse power lasers, various beam widths, various energies, and we do a lot of experiments with combinations of the different lasers, with the pulse power accelerator, and trying to get all these timed together, working well as the scientists and engineers are continually modifying and changing things. It's a big challenge. So we had to redo the entire lasers control system because it came to us as a prototype from the National Ignition Facility, and we had to get it integrated both with itself functioning better, more reliably, and with all the other different systems that we have there. And so you can see a poster out there later on, along with other posters from our group that have more details on this if you're interested. So first we start with breaking things down into different timing regimes. So I'm sure most of you know this. You got your general purpose OS, Windows, Linux. It's very low reliability, but it's very easy to program for. And then you can move on to your real-time systems using Windows CE, different embedded controllers. Some use VxWorks like PLCs. And these give you a little more reliability. You can optimize it further and you can get your fast real-time systems, very fast cycle times, very high reliability. And if you need something even faster than that, then you've got FPGAs where you're literally programming the hardware itself. With this stuff, it gets a little more complicated. Most people have to learn another programming language just to be able to interact with them. And it takes a while to compile the bit files, but it's worth it if you need that speed and reliability. And if you want to go even faster than that, you could use delay generators or a network of delay generators. A lot of places use it for their timing triggering cycles. It gets you your super fast timing, very low jitter, and you can't program a lot into it though, but you can make sure that when a trigger comes in, another trigger will come out later with very high reliability. So when we get our various systems that people tell us to build, we start with requirements. You know, what do you need for timing? So we have very high-level sequence coordinator systems. It doesn't need to be fast, but it needs to be flexible. We need to change out a lot of stuff. We need to get people to, give us the requirements up front, which they never do. So later on, we'll figure it out, we'll modify it, get everything working. Some systems, like charging systems, are very slow. You need real-time stuff, but it doesn't need to be fast. And then trigger sources have to be very fast and reliable, which things that are reliable, such as safety systems, interlocks, charging systems, laser safety systems. You've got all this stuff that needs to be very highly reliable, especially when it comes down to troubleshooting stuff later, so you get your data logging systems built into that too. Flexibility, again, mentioned before, your whole top-level system, it has to be very flexible, so you can modify the sequence. Sometimes they want one laser, sometimes they want 3 lasers, sometimes they want one laser with a pulse power system and a diagnostic that they just built yesterday. And then you've got your wide variety of hardware, custom things, benchtop things, embedded controllers. And you need to integrate all this together at different timescales to make it work functionally and reliably. So we break it down in different control hardware choices. We've got our low-speed, non-real-time user interface. Works pretty well for that. People don't work in real time. And then we've got our actual real-time stuff, pressure sensors, measuring voltages, and things that need to be reliable, need to be fast, but don't need to be as fast as the actual triggers themselves. For that, we'll go into FPGA. You can really quickly do a bunch of complicated logic, such as verifying interlocks, verifying your amplifier states, triggering flash lamps at just the right time, and then your delay generators, which give you that like high precision, here is the trigger. You need to do the event right now. So we break all this down into our software architecture. High-level coordinator, custom sequences, very easy to troubleshoot, easy to modify. Your low-level systems, all your embedded controllers spread out through the facility. Each one has a specific task or set of tasks that it needs to do on its own, and the coordinator can just tell them to start or stop as necessary, check on them as they go through their process. We typically use TCP/IP to push a command to each of the individual subsystems, tell them to do something right now, and then we can pull for status later using publish-subscribe protocols. So it's a little higher response time, but it's very easy to plan for that kind of thing as you continually check on it through the whole shot sequence. Here is this very professionally put together diagram. You can see you've got your user surrounded by all the screens, so you can kind of see what's going on. Doesn't necessarily have to interact with anything. That's all managed by the coordinator shot sequence stuff. But all that stuff talks to the shot control system, which handles all of these high-level sequence tasks. It talks to all the various subsystems, which will each control an embedded controller or a device spread out through the facility, and kind of takes care of like the low-level tasks that need to happen during the sequence, checking on things, making sure things are charging at the right rate, making sure that your delay generator is ready and configured and will trigger when you expect it to and how you expect it to, and any number of other subsystems. In this case, we had like 30. So, summary, putting together systems, you want to understand your timing requirements for the hardware because you can't fix that later. It's very difficult to basically take a bunch of systems and replace the entire hardware component and hope things run smoothly. You want to select your ecosystem based on secondary requirements, whether or not you're going to use LabVIEW, EPICS, Python, C++. It just depends on if you have programmers that understand that stuff. You architect your software appropriately to satisfy your timing, reliability, troubleshooting requirements. Easier to troubleshoot, faster you can build it, faster you can test it later. And above all, just try to keep it simple. So if you have any questions, now would almost be the time. There's my contact info, and we will have posters out in the hallways if you have more questions after this.
Thank you, speaker. So, do we have questions for the speaker?
No questions.
So I've got one, Aaron. What kind of software architecture, software types? Is it LabVIEW? Is it kind of EPICS?
Mostly we use LabVIEW. A lot of it we build in-house just so that we don't have to rely on external libraries. We've had to upgrade a lot of old LabVIEW stuff that was written based on external libraries. And the external libraries at some point fell into disuse. So when we build a system from the ground up, we make sure that it's all one type of software, all supported, and has no external requirements that we can't fix later on.
And what kind of size is your control staff?
We have roughly 4 or 5 people who do LabVIEW, okay. And the entire department is about 12 people, which includes operations. So not that many people, but we got a lot of systems to support.
Any other questions? Okay, well, let's thank the speaker.